So what I want to do now is really shift gears and go more into the applied side and show this how we use the large language model agents on the application of atomistic simulation. So what we do in our work is really trying to go from the simulation side to predicting or to materials design, and we use workflows and more recently large language model agents to achieve this. And that's also where my question came from, right? So we now build a large language model agent system. We call it DREAMS. So it's for density functional theory, research engine for automated materials screening, where we demonstrate what is the current state for specific quantum mechanical simulation and what agents can already do. So as a user, you can ask a question that you would also ask your expert or your fellow colleague. The agent then generates a plan and modifies it depending on the priorities. And then behind the supervisor agent, we have a whole team of different sub-agents that do the individual tasks. Right? So we have one agent for our quantum mechanical calculations. There's one agent for the convergence. So in principle, quantum mechanical calculations are always exact. But if you choose this too small basis set, then it's going to be hard to describe the material properties. And then the other part is obviously the interaction with the HPC part. So that's also, there's a separate agent that's taking over this part. What we learned in this study was that it's not so easy to have the agents keep track of their work and really keep an overview of the tasks and the different subtasks. So to address this challenge, we introduced a canvas where the agents can leave messages for the other sub-agents. So basically the worker agent maybe says, okay, these are the calculations that should be done. It leaves a section there that then can be picked up by the HPC agent. And then the HPC agent can do the next steps, maybe submit these jobs, afterwards store the calculation, where again the DFT agent can then pick those up and work with the data. Right. So for us, the important part to go beyond the limitation of a single agent and with maybe multiple tools was that for the team of agents to really have a structured way of communication, which we achieved with this kind of canvas. So now in the next few slides, I want to show a bit what we can then achieve in terms of concrete simulation results. All right. And what was important for us here was that we see a couple of papers where people demonstrate the capabilities of their agents on benchmarks that they also come up with, which we feel is a bit sketchy. If you design the benchmark, you shouldn't be the one to test the agent on this. So what we chose was a benchmark that was already previously used in the community, and we measured the performance of our agent on this kind of benchmark. Right? So we sent the request. The agent then really nicely plans the workflow, and I completely agree with the previous speaker, right? So there's not much of a difference if we build a workflow as human or if we have an agent building the workflow. Right? So the supervisor generates the plan, the DFT agent then structures the simulation and prepares the input files. That's where the HPC agent takes over, handles the job submission and the communication to the HPC part, gets the first results back, gives them to the DFT agent, and so on until we get the final result. If we now take a look at what the results that we get, so that's what we see here. So for us, as the one very important part, as I mentioned before, are these kind of convergence checks. So we can see that it tested different kind of basis sets until it agreed with the predefined limit that the user was aiming for and did this for different properties. And in the end, when we compare the prediction of this agent to predictions of experts in the field, we see that the scatter is only around 1%. And that's really important because it highlights for us that this kind of a very standardized regular DFT task can now be done by an agent. And as an expert, I have no chance to say, was this now done by another fellow agent or was it done by a large language model system? Right. So for me, as somebody who's very focused on the method development side, this really allows me to focus more developing new methods. And if an experimental colleague or another colleague wants to use my methods, they can do so through the agent interface. And by having these structured workflows, we can make sure that they always get the right results and the same level of quality that they would get if a DFT expert would do the simulation for them. So then we ask ourselves, okay, why does it work so well, right? So why does it work so well for these kind of DFT simulations? And I think the important part there is that DFT is really like a long time coming, right? So this method development started roughly 50 years ago. In particular, over the last 15 years, there was a huge effort in different high throughput screening projects, really going over the whole periodic table, trying all the different combinations, and in particular, developing also a toolbox for this kind of high throughput screening. And when these tools are available and the workflows are available, then building the agents on top is very simple. I just want to say this here as a disclaimer. If you may to try to apply the same to a different field where there's maybe not so much experience in high throughput screening, then it's most likely much harder to apply the concepts of large language models agents there. That's really this kind of high throughput screening part is the main driver that now allows us to really provide these agents and have our experimental colleagues trust in the capabilities of these agents. So now going beyond just individual static calculations at zero temperature, we now want to look at the finer temperature properties, and the most critical one there being the melting temperature. We calculate the melting temperature by having the equilibrium between the solid and the liquid structure, as I show this here. And again, we have a very standardized workflow here, right? So we see the user inputs, they are marked in red. We have simulation steps, we have steps that modify part. And then the important part is the analysis always in between and the corresponding feedback loops, right? So for us to go from a regular workflow to something which is autonomous, what we find is that we have to introduce a series of new detectors. So for example, a detector to figure out what's the ratio of solid and liquid structures, or one that figures out when there are voids forming, in particular in the liquid phase. Once we have those detectors, this workflow can really be applied to all different kind of, in this case, interatomic potentials, and really screen over the periodic table. But the highlight here is really to say, first focus on building the analysis in there, and then with this analysis, then you are able to automate the workflow and it really submit it and forget. All right, so that was the part here. Now, if we progress even further, right? So the next step is then to see if we can apply the same also on the experimental side, right? So here we try to bridge this gap and see what's possible there. And what our colleagues at a local university are now able to really produce already these kind of nice wafers with different compositions. And so the challenge there is less of producing the samples, but really more on the measurement side. And I speed up a little bit. What we see there is that the measurement is now really the time-consuming part. Right? So we have these nice chemical gradients in our sample, and then we typically would just do going one line after another and do all the measurements. And that can get very tedious, right? So if we think about like an XTID experiment, the screening of one of these material libraries can easily take 12 to 14 hours. And so that's where we thought, okay, can we now combine this with our simulation expertise to then run the simulation and basically accelerate the process of the measurement. Right, so that's what we show here. So we show now, we do DFT calculations to have exactly the same level of accuracy with our experiment, and then combine both in a Gaussian process. First, we did it naively on the same level, and then we primarily used the simulation to optimize the DFT hyperparameters. And with this, we reduced the number of measurements by nearly 1 order of magnitude. And with this, I already come to the conclusion. Right, so I hope I was able to show you that the large language model agents greatly benefit from the workflows. For us, it really is a direct connection to the previous work on the workflow frameworks. And we're now very interested to go to the experimental measurements and connecting this also with Python functions and really have those experimental parts as part of our workflow. With this, I'd like to thank you for your attention.